Hello everyone, and welcome to another Webinar Wednesday brought to you by the Concrete Preservation Alliance. Today we are talking about pipe dreams made real, non-destructive techniques for assessing and maintaining reinforced concrete pipes. This is the second of a three-part series focused on the use of non-destructive technologies to assess concrete structures. This presentation is brought to you by the Concrete Preservation Alliance. It is a growing coalition of organizations committed to advancing best practices in the field of concrete preservation and infrastructural renewal, working together to promote education and awareness of concrete repair industry standards, new and innovative corrosion prevention technologies, and sustainable construction practices. We draw on our exceptional members to provide speakers that will use their industry-leading expertise to educate and bring awareness to the concrete repair industry. You can find the recordings of today's and previous presentations along with their slides on our website here at wesavestructures.info under the Events tab. This is also the home of our Environmental Impact Calculator. So this is a tool that you can use to create a customized preservation impact statement based on your inputs. So you simply input the volume of the concrete that you preserved into the form, and it'll automatically populate to show you an estimate of the amount of emissions, waste generation, and environmental benefits of concrete preservation versus demolition. You can also print this to a PDF to allow you to showcase the difference your decisions make in preserving the resources of our planet and how you are striving for improved sustainability. A challenge to you all before we start, we have a Q&A portion after the presentation, and we are giving away a $100 Amazon gift card to the best question asked. Due to our platform not tracking our attendees' information, you'll have to provide us your name when asking your questions, so you can be considered for the prize. Otherwise, we won't be able to find you to give it to you. You can ask as many as you like, so ask away, and the best question will be picked by your presenter. And your presenter is Mr. Bill Horn. He's the president of NDT Corporation, a non-destructive testing company based in Sterling, Massachusetts, evaluating all types of infrastructure materials, including concrete, timber, steel, masonry, asphalt, oil, and soil and rock. Working in the transportation industry as a registered professional engineer for over 25 years, Mr. Horn has experienced successfully managing complex projects for many private governmental clients, and is published in the field of non-destructive testing and geophysical investigations. He's also considered a national expert on FHWA's compliance metrics for scour critical bridge evaluations. He graduated from Clarkson University in Potsdam, New York, and obtained his BS in civil engineering in 1988 and an MS in civil engineering in 1992. And with that, I'm going to let him take it away. Bill.
Fantastic. I'm going to take control. Ben, can you hear me okay?
We can hear you great, Bill.
Fantastic. Let me just share the one here, and we will get rolling in presentation mode. Do we have an outline starting us off, Ben? Are we looking good?
You look good.
Fantastic. Well, thank you, everybody, for the opportunity to share some knowledge on testing PCCP, pre-stressed concrete cylindrical pipe. There's some concrete tanks we're going to talk about. And some case studies. So the title of this is Pipe Dreams, and boy, in a dream world, we would have a durable and reliable pipe system that's cheap to manufacture, easy to install, never gets damaged, resists all the bad soils it might be sitting in, never requires maintenance, is going to notify everybody if there's any leaks or problems, will prioritize itself with whatever needs to be done. That's not really a pipe dream. What we have is a series of pipe systems that have been in the ground for a long time, and the system is only as strong as its weakest link or stick or individual pipe sections. So what we have is a lot of the reality is pipes break, and when they break, they not only waste water, they can launch boulders and impact the community, undermine roads, and really certainly cut off the water service. That's the pressure Here's another one on a closed circuit TV, the event, a lot of dust and mud, and then all the water flowing down the street. Here's a slow motion version. Look at the power of that explosion. That's the pressure that these systems are under. They happen in urban environments and they happen in rural environments. And that is because we have a system that has been installed years ago, and it requires maintenance, just like everything requires maintenance. Your house and your car and your pipe systems require maintenance. I found this fact here that there's about 850 water main breaks in North America every day. That's a lot of pipe failures. That's a lot of wasted water. And that's where the engineering community and water authority owners can proactively minimize this concern. Pipe failures are just that, holes in the pipe, but they happen unexpectedly and they will render the system virtually useless down until it gets fixed. Chances are that people are going to be without water or without wastewater, depending on what pipe system we're talking about. The damage sometimes is not a gaping hole, it's breaking in some of the reinforcing, and I'm going to describe how pipes are constructed. But here you can see there's a close-up of some degradation of some pre-stressing wires in a particular pipe section. We've had the fortunate opportunity to test pipe sections in service as well as pipe sections forensically after there have been some failed pipes. And there's an outer coating. I've got a diagram of what PCCP is, but this is the damage that we're trying to identify early on by testing the pipe from the inside or from the outside and catch it before it breaks. You know, the deterioration can start with installing a new piece of pipe. Maybe there's a rock or some sort of anomaly that this pipe is sitting on. It should be sitting on good bedding material, but if there's a point load and then the pipe surges with pressure changes over time, that can produce cracks, maybe at the spring line, maybe at the point of impact of where the improper bedding material may be. And as the cracks propagate, that can be an overload and a weak link for that pipe to break. Again, there's a little pinhole that shot in the middle is where there was a hole in the pipe, and then that corroded the reinforcing wires even more rapidly. On the left is a cross section of PCCP. There's an inner core, a steel membrane, an outer core, which is thicker. And then the whole thing is wrapped in pre-stressing wires. And then there's a mortar coating on the outside to protect the wires from degradation from the soil. Over on the right-hand side is an area that we would identify. We're inside the pipe here using clock positions to delineate where the deteriorated conditions do exist. But we'll talk with some definitions first. Pre-stressed concrete cylindrical pipe, PCCP, inner core, bonded, and it should be in compression. The steel membrane, that's actually the pipe itself. There's an outer core that again should be in compression because of the pre-stressing wires. And a mortar coating on the outside to keep it all confined. Now, bar-wrapped pipe is a close cousin. There's a little bit different reinforcing configuration, but it is very, very similar to PCCP, again, pre-stressed concrete cylindrical pipe. We've got a schematic here of the pipe itself. That inner core is the brown area of concrete. Then there's the pipe itself, the cylindrical pipe. That's really what transmits the water. Concrete, 3, 4, 5 inches thick, depending on the gauge of pipe. So we have the steel cylinder sandwiched between two layers of concrete, but then at those pre-stressing strands that are wrapped around the pipe, putting it in compression. And that's where concrete, when it's in compression, gains its strength, as long as the pre-stressing wires maintain their integrity. When they start to break, that's when there's problems. And that's what those images I showed you in a couple previous slides. It's where those pre-stressing wires break. And then on the outside, there's a mortar coating, and that is designed to protect the pre-stressing wires. So the steel membrane is really the pipe and the pre-stressing strands make it stronger by putting the concrete inner and outer layers in compression. So a little introduction. I wanted to do a little more of history of PCCP and water systems, just to get context, I think, for everybody. We're all used to turning on the faucet and having water come out. That's expected, just like we want to turn on the light switch and have power come on. As I mentioned before, our systems are very old. The cylinder is what really contains and transfers the water. We've just strengthened that. I talked about the pre-stressing wires. Our infrastructure, though, is 40, 50, 60 years old in some instances. A lot of development happened back in the 50s, kind of like the interstate system. I found a fact that says there's almost 150,000 public and private water authorities in the U.S. Now, the ASCE, American Society of Civil Engineers, grades all of our infrastructure, and a C- and a D+ isn't. But to give perspective, there's over 2 million miles of underground pipe. Now, not all of them are PCCP, I understand that, but just a magnitude, almost another 1 million miles of wastewater pipe. Usually the water pipes are under pressure, wastewater pipes often are gravity fed, and we'll talk about those. Now, water authorities do recognize their need, and they're trying to implement programs and replace deteriorated sections. But when you're replacing 1 to 3 to 4, 5% of the pipelines each year, it takes a lot of years to upgrade the entire system. I found this statistic also, 4 different things. The light tan and the kind of dark, the purple are related to water systems, water treatment. The tan on the bottom is the network expenditures, the pipes. The burgundy, 2 up, is the treatment plants. That's a smaller cost, but it still is growing as we look over the past 10 years. The trend is to increase the costs, but the network is a larger expenditure than the treatment plant itself. That holds true for wastewater. That kind of red-orange gap is the system, and then the blue up top is the plant for wastewater. So piping networks, this is only through 2016, that trend is continuing and maybe even expanding based on the age of the infrastructure. So what are the pipe concerns? The American Water Works Association has defined a series of concerns when looking at pipe networks. Overstressed pre-stressing wires. They pulled them too tight when they made them or when they wrapped the pipe. And there's high stress and high strain now in this tension of the wire, and they can break. Hydrogen embrittlement for the wires and the concrete can make it more susceptible and less durable. As far as hydrogen sulfide, a little bit more aligned with wastewater. That's where the inside of the inner core of concrete can actually get thinned out, and a reduction in the thickness based on the interaction between those hydrogen sulfide gas fumes, if you will, and the concrete. Corrosion, if there's a little pinhole or a leak, the steel is going to corrode and get weaker, and the wires could break. And as I said before, it's the pre-stressing wires that keep it all together. It could be damaged during installation, pushed around with a bulldozer, sitting on a rock, improper bedding material. Somebody can dig into it and damage it. They're drilling a hole or a soil boring or digging, so they'd be surprised how much third-party damage actually occurs. An overloading condition, that could be both from a surcharge condition, piling up soil on top of a stockpile area, and there happens to be a water pipe below it, or just the surges, the pressure surges within the pipe system during its normal life cycle. But there's evaluation programs. I've kind of got a phase 1 and a phase 2 here. The phase 1 is can be done in the office early on, just a desktop risk assessment. What are the existing conditions? What was constructed? What was designed? Maybe we have some drawings, maybe we don't. And wanted to Also look at kind of an office-based screening. Let's do an inventory. Let's find out where all of our pipes are, where our valves are, and where the redundancy in the system. Maybe we can use another system to take one offline and repair and replace it. A design review and prioritization. Where are the weak links? Finite element modeling plays an important role in this as far as identifying pipe performance, weak pipes that don't have the factor of safety we're looking for, and where there are ones that do have the factor of safety and are functioning just fine. Documenting existing conditions is important, and again, valves don't always work. I hope that's a good takeaway for everybody here today. But a more in-depth evaluation program would require some field inspection. Now, these costs go up drastically when we are looking at the pipe. You can define where some leaks are. You can put these balls, floating ball sensors, if you will. They listen for where the leaks are. They go inside the pipe and they travel from A to B, and then they are recovered and the data is evaluated. Inline visual assessments. We're talking robots, closed circuit TV, even sonar imaging to identify visibly what the pipe looks like and how it is performing. Now, a more detailed approach is a condition assessment. What's the integrity of the concrete pipe itself, whether we're testing from the inside or from the outside? Sounding it, just kind of hitting it with a hammer, or in what I'll talk about a little bit more here is non-destructive testing. There's also some electromagnetic assessments that can be done from the inside, and the mechanical non-destructive testing is what we're going to do a little deeper dive on here this afternoon. And our quest is to understand how energy waves propagate, what the velocity of those energy waves are, and what the frequency of that trapped energy in the pipe wall thickness tells us. These programs do take years to evolve and develop. What we're trying to do is the results of the assessments, find out where the cracks are. Are there wire breaks? Is the pipe leaking? Where is it leaking? How extensive is the leak? From the engineering analysis, what are the weak pipe sections? What ones have deteriorated over time and should be slated for replacement? You know, what's the risk? There's a cost of not doing anything, and that's having a system fail. Prioritizing certain sections for repair requires some redundancy, and maybe a secondary system has to be utilized, brought into service, or maybe even installed to get access to the primary system that needs to be replaced. And we have to execute these repairs or replacements, communicate with the public. They need to know what's happening. Okay, we're doing a flushing event, or we're going to be out of water, or it may be cloudy. So it's really important to communicate with the customer and then monitor these pipe systems. Once you have some baseline information and we can look at pipes, the same sections of pipes over different times, we can understand the service life, quantify the rate of deterioration in the system, and be a little more proactive with some of our implementation repair efforts. So now we're going to go into some pipe testing theory, how those energy waves, remember it was velocity and frequency information that I'm going to try to explain to everybody. Velocity information, how fast do energy waves travel? We know how fast they should travel in good quality pipe, and when they travel slower, we can quantify those pipe sections to be suspect and damaged, thinned out, or micro cracked, depending on what information is recovered. Reflected and refracted energy waves go through normal concrete and pipe one way and go through pipe with anomalies in a different way, and we need to understand how that amplitude of those that energy and that frequency, that energy is trapped between the outer part of the pipe and the inner part of the pipe, and that oscillates in between there, and we can understand the integrity of the pipe by how the velocity and frequency data of the inner core or the outer core or the whole pipe in general. Overall, if energy waves are going faster, they're probably going through a stronger material. And if they're going slower, they are going through a weaker or more micro-cracked material in the case of concrete. But with the pre-stressing wires intact, that whole pipe section should be acting in a certain compressional stiffness. And when those pre-stressed wires are broken, that section of pipe is no longer in compression. That has a big impact on how the amplitude and the frequency respond in the pipe. When we induce energy into the pipe, here's an example of some equipment. On the right, we have the energy source. It is an air gun with a special steel bearing hooked up to a tank of compressed nitrogen. So it's a very repeatable high frequency energy source every time we pull the trigger. And then our sensors or our listening devices that are in contact with the surface are on the left. This happens to be a 4-sensor array where those black spring-activated nubs are touching, in this case, concrete wall or a concrete pipe. I have examples of that. We know the distance from the energy source, and we know the distance between the 4 sensors. Let's call them channel A, channel B, channel C, and channel D. In this instance, is about 6 inches between the first two, and then 12-inch distance between the other ones. So that's a 30-inch lineal distance of data that we're going to get every time we pull the trigger on the pipe. So how do these energy waves propagate? We've got a surface energy wave. I often use the example of dropping a pebble in a pond of water and looking how the rings radiate out on the surface. We can see that, we can visualize that. Well, when we hit the surface of the pipe, inside or outside, with a ball projectile, steel bearing, there's a surface wave that travels along the surface of that pipe. That velocity is picked up at sensor channel A and channel B and channel C and channel D. So there's a horizontal surface wave that we're interested in. And then there's a vertical component. That energy wave travels down to the boundary condition, the inside of the pipe, or maybe the inside of the debonded layer of pipe. And we can get information. It gets reflected, that energy gets trapped in between those boundary conditions and oscillates at an amplitude that we can see and a frequency that we can calculate. So what does the data look like in the field? There's a lot more going on here than a lot of squiggly lines. We have a compressional wave, which is the first arrival of our energy waves. We have a shear wave that kind of has a double hitch on it. That's its own little fingerprint. A Rayleigh wave follows. And then that vertical red dotted line is the first arrival. And then we get a first arrival on channel A. We have a first arrival on channel B. We have a first arrival on channel C and D. After the first arrival, there's a lot of energy that's bouncing all over the place. But the first arrival on each one of these, and these are in milliseconds, nanoseconds almost, happens very quickly, but it does happen in a precession. And by recording this information, we can delineate the condition and the durability of the concrete pipe. We collect data according to 2 different ASTM procedures, pulse velocity measurements and impact echo measurements. That's that horizontal surface and vertical reflected measurement. Both are in the ASTM concrete standards. 597 is pulse velocity and 1383 is the echo reflection. We use both of those. So if we look at over on the left-hand side, we're getting the full pipe thickness based on the reflected energy. And that maybe that's 6 inches, 5.5 inches, whatever it may be, because the concrete and the pre-stressing strands and the steel liner are bound together. If there's a debonding or a delamination of those pre-stressing strands from the concrete in this diagram, that thickness frequency is going to change. Maybe it's going to go from 5.5 inches down to 2 inches. And it's still the same pipe, but that tells us that there's an air gap, and that air gap corresponds to a debonding or a delamination of one of these components of the pipe. Now, the velocity information is valuable, and we can equate concrete strength. I'll say it again, we can get concrete strength from sound waves. So the velocity, 13,000 feet per second, if it's that far right line on this curve that we've developed over years, corresponds to maybe about 6,000 psi, and this holds very accurately when maybe concrete cores are taken to supplement or complement the calculated values, calculated compressive strength values of concrete, again from sound waves. Talk about the testing. Now we're testing inside. Larger diameter pipes, if they're out of service, can be tested from the inside. We can put our equipment on poles and use them. We have little carts to collect hold our computer data, and even sometimes hold us and allow us to move in the pipe. Sometimes the pipes 54 inches, 48, 42 is probably about the smallest pipe diameter that we can get in, and the smaller ones, they can be tested from the outside or with some remote robots or closed circuit TV imaging. A few more examples of testing from the inside. There you can see the equipment on the left. It's portable, it's battery operated, it's on a little cart and just rolls with us. We have the gun on a pole extension with a trigger that fires the steel bearing from a distance, and then we have the sensors. There's a little spring action in those 4 sensors that touch the pipe wall, and we're measuring the velocity, surface velocity, and that reflected energy of the pipe, hopefully as a whole, or depending on how it comes in, the inner core just, or the outer core, or where some delaminations may be occurring, or even pipe wall thinning. Now, the smaller diameter pipes, or if we're just not going to take it out of service, we have to have access to the outside of the pipe. Here's some simple excavations where we are testing. The energy gun is there, the sensor array is there. We would mark out 1 foot increments on the pipe section that we're testing, and we try to collect data on the clock, the 12 o'clock position, the 11 o'clock, 10 and 9, 1, 2, and 3. Sometimes during excavation, we still want to have the bedding material supporting the pipe. So generally, we wouldn't get information all past, 3 or 9 o'clock, just unless it's pretty complex, and then you have to support the pipe, and that can get a little tricky. But here, looking down at with the other ones, were a relatively shallow excavation. Here, there's some shoring boxes that are in there. We would want to make sure all excavations are up to the OSHA excavation standards. And we mark out the pipe, and on the left we're at the 12 o'clock position, and we have access to the 1, 2, and 3 and the 11, 10, and 9 over this limited section. If we can open up a 20 or 30 foot section of pipe, we may be able to have access to maybe up to 3 joints, 2 full sections of pipe, and we can strategically pick these excavations along the system. And maybe we can get some information on 5 or maybe even 10% of the system. And based on the information we have, we can glean the integrity of the overall system and understand if it's more or less than what it was designed for. So the field data that we're getting, we've got the velocity measurements on the left, and we've got the frequency data on the right. And there's a whole process to analyze the data that goes into our investigation. We have to be on site, we have to collect the data, make sure it's good data, and then go analyze the data and provide an easy to understand process of what is shown in there. And legends of green and yellow and red are often helpful to help explain where the weak sections of pipe are, not only within a section, where within the section, 11 o'clock, 8 feet down, or 3 o'clock, 4 feet down from the joint, or whatever it may be. So it's very important to document the condition of the pipe, get the stations right, know which section of pipe we're on. That's where some of the desktop inventory information can pay a lot of dividends. We're tracking the compressional wave velocity, the shear wave velocity, the frequency, and we also measure thicknesses of the pipe. All 3 of those are the meaningful information that goes into providing an assessment, condition assessment of the system. So the results we get from this data, we get the thickness of the pipe, thickness of the mortar layer, how the inner and outer core are performing. Is there delamination between the inner and outer core from the Steel cylinder, that's very, very important. Is the pipe in general in compression or is it not in compression? If it's not in compression, the wires have been compromised. Condition of the pipe at the ends and the joints, very, very important. If there is a wire break, there's probably some corrosion that's going on. There may be a leak associated with that, and that corrosion can continue to worsen. We talked about overloading conditions before. There's bedding material that should properly be installed and the pipe placed on that bedding material. But there's also pressure surges within the system when the system undergoes changes, is turned on or turned off, and they have an impact to the overall integrity of the pipe. Is there cracking? Is it visible or is it non-visible? That's where the velocities of these energy waves come into play. We kind of know what little or no cracking should be, and from our experience, 13 to 15,000 feet per second, that's probably well-functioning pipe. If that velocity drops down to, say, between 11 and 13,000, that could correspond to some micro cracking in the pipe. We can identify that maybe with a yellow coating, making it easy for the engineers or the water owners to understand where the weak sections are. And if it's below 11,000 feet per second, it's even more compromised, and additional cracks may be of concern. Back a little bit further on the data analysis, back in the office, we've got the normal attenuated signal. Those are the three examples on the bottom. That's just what we saw before. We have the shear wave, compressional wave, and the Rayleigh wave. And then the amplitudes change. Those three on top, that's a lower frequency, a higher amplitude, an irregular amplitude. That's a hollow sounding pipe. That's got something that's delaminated. And interpreting those conditions is very, very important. That's where our experience in collecting data, interpreting data are so important. Now, pipes do degrade over time. And the way we can know that is when we're evaluating the same pipe section over two different periods of time. And then once we have that opportunity, 2 or 3 different data points over 2 or 3 years in between, we start to see the changes in the pipe and can start to predict the service life or deterioration curve relative to the pipe. Sometimes there's, anomaly ratings that are kind of a weighted average of the type of pipe and the condition and a few other variables that is kind of a weighted average that can be applied to all the different systems to see where the priorities are for replacement. This particular one happens to be a pipe that was a 96-inch diameter pipe that it did change pretty rapidly over a period of 6 to 8 years. It was doing fine in the 90s for 15, 20 years, and then kind of reached an area in its service life where it was starting to weaken. And then once maybe there was a leak or something changed the durability and the condition of the pipe, it started to degrade rapidly over time. And again, things can change over time. Here we're looking at 2 sets of data. Okay, on the right is 2019, on the left is 2021. So over on the left in 2021, we've got some weak areas, lower velocities. They weren't there in 2019. So in 2 years' time, there was some drastic changes. 2 years' time beyond that, those changes can continue to deteriorate the integrity of the pipe, and that could result in a pipe failure or at least a lower factor of safety and hopefully a higher prioritization for repairs. So I'm going to change gears here a little bit and been talking a lot about pre-stressed concrete cylindrical pipe. There's other types of pipe, and ground penetrating radar is very valuable. It doesn't work with PCCP because of that steel membrane. The steel cylinder really shuts down the electromagnetic energy. We'll be able to see the steel cylinder, but we won't be able to penetrate past it. But in typical reinforced concrete pipe, gravity-fed wastewater pipe, we can use GPR to very effectively understand the condition and what's going on. The one big takeaway for GPR that I want everybody to remember is that there's different frequency antenna. Okay, some of the higher frequencies, 1500 megahertz, 2700 megahertz, they're ideal for locating reinforcing embedded in concrete. Some of the lower frequency GPR is designed and ideal for locating subsurface utilities or anomalies. That's the 200 megahertz, 400 megahertz. GPR tries to measure basically the electrical density of a certain material by having that energy be reflected off of it. Always a bit of a trade-off between resolution of the GPR data and the penetration of that energy. But the energy is looking to be reflected off conductive material. Rebar is conductive. Air and water are conductive. Salt and salt water are very conductive. So we do have some limitations. If it's a brackish environment or salt water tables that are high, that is going to impede the ability for the electromagnetic energy to penetrate that soil condition because of the conductive salt or salt water that's around it. A couple of GPR antenna examples. On the left is the larger orange box. That's a lower frequency, 200 megahertz antenna. Really good for locating rock depth, rock profiles, not just one particular data point in rock elevation from, say, a soil boring, but rather a profile, as long as it's relatively shallow. In dry granular soils, the 400 or the 200 megahertz can ideally penetrate 8 to 10, maybe even 12 feet in granular soils. Now, if there's moist clays or saturated clays, that penetration may significantly be reduced. We might only penetrate 4, 5, 6 feet into those conditions. And if there's salt residue in the soil matrix in and around coastal areas, that salt residue can impede the ability of the electromagnetic energy to penetrate. In the middle, 400 megahertz is trying to identify leaks. Water is conductive. So where we find the water, we know there's a leak in the earthen dam. Or where there's a sinkhole, there's an energy boundary or a GPR boundary that's picked up. If there's a leak in a pipe, maybe some of the sediment has been transported away from the pipe and you generate a sinkhole. Small scale sinkhole in a parking lot or something, not the large scale ones that sometimes we see down in the southeast. But if it continues on, or if there's a large break, we could obviously have a lot of sediment that is transported. The 900 megahertz on the left here is on a pole. We're in a aqueduct feeding water to a municipal water area from a reservoir. The frequency goes up. The 1500 megahertz handheld mini is very often used to locate reinforcing in concrete. And there's a newer version, the Mini XT. Is a little more modern. That's a very effective tool. There's also a little palm extension that plugs into that. We do want to cross over the reinforcing or the conductive material to find it. And what does it look like? It looks like parabolas. On the left here, the GPR examples are shown and the signal is attenuated on the right. And on the right image, trying to verify the pipe wall thickness. I've got an example of QA/QC construction for pipe. GPR was used to verify the pipe wall thickness. There was supposed to be a drilling spec that was going to drill through the top of the pipe at 12 o'clock to verify it was 12 inches thick. And we were approached by a contractor to say, hey, well, GPR, can that replace the drilling spec for this? And we said, yes, it could. We need to keep the GPR antenna in contact with the pipe. So once we fabricated a little spring activated lever to keep tension on the pole, we just drove through about 2 miles of pipe in the period of about a day and did some validation core drilling where we thought there was anomalies. They were spot on, and this GPR replaced the drilling spec. I did the GPR scans are showing where there's a strong reflector. That's where there is a big boundary condition, an air gap, if you will. Do want to share a little bit on tank testing. Obviously, we want to look at the plans, make sure that things were built the way they were designed. There's visual inspections that can be done, testing and sampling. Some lab testing is very valuable, and we want to get some representative data on the whole tank and then do a deeper dive on certain sections of the tank. Half cell readings are very valuable. That's ASTM C876, and that looks at the probability of corrosion of embedded rebar. We need to make a connection to the black steel and then just measure the change in voltage by touching the surface with a wet sponge. So we have to locate where the rebar is. GPR is going to help us do that. We have to drill in and connect it to the steel. And then we just touch the concrete surface in a 2-foot grid or 3-foot grid or whatever may be required. Tanks, again, are often in a confined space environment. And over on the right, maybe it's open to atmospheric conditions, but this tank may be collecting water from mixing or from washout or cleaning operations. We need to have access to the tank, so sometimes man lifts are required to do a detailed investigation of a certain section of tank and also try to get some information on the tank perimeter itself. On the left is our impact echo pulse velocity. On the right is our GPR. It's a good 1-2 punch to evaluate concrete. And there are instances where coring provides additional information. We're not going to core through, this is a wet core, we're not going to core through the pipe wall, but we'll core maybe halfway or 3/4 of the way. We'll fill that. Or if there's a baffle wall between two parallel tanks, we may want to core down through that wall to quantify some of the cracking. I got a few case studies that I'd like to go through here. Really showcases the 3 different types of data. Frequency data we talked about. We try to make it easy to understand where the frequency correlates to severe conditions versus minor changes in the integrity of the pipe. Wall thickness, that's a measurement of that thickness frequency that I talked about, and we can identify where the original thickness was supposed to be around 6 inches. We get down 5.5 inches, 5.25 inches, and we can use a legend to identify color code, if you will, where some of the weak sections are. Same with velocity. Compressional wave velocity helps us identify where there are deteriorated sections of pipe, what's normal, what's got minor deterioration, and what has severe deterioration where maybe some of the wires have broken. Continuing on with the case studies here, this was an interesting one. There was a steel liner that was put in a hydro facility in a concrete draft tube, and then the outside of the steel liner between the steel and the concrete, about a 1/2 inch gap, was grouted, and that was supposed to be bonded between the two. That was the repair strategy. We were testing from the inside. If we got our signature amplitude on the left, that's a well bonded, good grouting job. If the amplitude opens up on the right, that had some voids present. That needed to be topped off a little bit more, so we were able to quantify that right on site. One interesting thing, NDT has got a collaborative partner, ASI Marine. We have mounted our impact echo pulse velocity testing equipment on an underwater ROV. We are pretty much the only company that I know of in the world that has this capabilities to do concrete integrity testing in remote pipe situations with an ROV. Has to be launched down the access point into the water. It does its sonar, visual imaging, and it does condition assessment of concrete, compressional strength and thickness of the pipe. We set up a command central to operate the ROV and to look at the data that's being collected, and we also want to be on site to make sure that we're collecting accurate data. Another tank condition is looking at cracks of pipe, and we can determine how deep those cracks are by how far away our energy source and sensors are from the crack origin. Here's some another case study of some tanks that are taken out of service during an outage. A mixing tank, a flock tank, a settling tank. Again, on the left, we've got the impact echo pulse velocity and then the high frequency GPR put together. That's a good condition assessment. This was a riser and a reservoir. There was no plans available. Nobody knew the reinforcing of the concrete riser or chimney. So we were able to determine the reinforcing. We were able to get concrete strength measurements above water and below water because our system is waterproof. We put it in the hands of divers all the time. And we assess some of the outfall pipes as well. A little bit about hydro. I did the draft tube example and we test concrete draft tubes, but spillways, we can do a condition assessment on the concrete spillway and then look below the spillway to see if there's voids beneath the concrete. The low frequency GPR is going to help us understand where those voids are. So the slab goes down to about 20 inches at that horizontal white line, and then there is a void below that, a 10 to 20 to 18 inch void below that, and quantify that. Interesting here, just to delineate the difference between surface testing and through testing. With access to both sides of a concrete member, we can do through testing. So with the energy source on one side, we have the sensors on the other side. As long as we know the horizontal and vertical position of our energy source and sensor, we can test right through this concrete buttress, happened to be about 8 feet wide, and get the concrete strength, the core concrete strength. The outside was much weaker, the core was much stronger. So I got a couple summary slides here, and we'll take some questions at the end. The conclusions are there's a lot of good asset management programs and plans that are out there. They are in effect and working right now. Assessing the condition of pipes, that is possible to do. We're trying to quantify cracks, corrosion, delaminations, and wire breaks. The remote data collection and surface testing is good. Monitoring helps for being proactive and replacing, but we've got a lot of old pipe systems, and the risk of not doing anything is pretty severe. Our systems are reliable. We want to keep them reliable. They are cost effective with proper identification of where the weak links are. Everybody's aware now of the importance of installation procedures and to get the proper bedding material. If there's a corrosive environment, some bad soils, we can bump up the durability of the pipe section in that area. We can do the testing to understand where the upgrades and the prioritization of repairs need to take place. And we can monitor these to identify leaks and see where pipe sections become weaker and need to be replaced. And the risk of no action is pretty significant. But again, the chain, the system is only as strong as the weakest link. It takes one pipe section to break and the whole system can go down. But there's decades of engineering experience that we've had on this. Yeah, it's all about the water. Let's not forget about that. It's one of our most valuable resources, and we should treat it very wisely. So a lot of good and innovative technologies, big data, a lot of large data files that we're analyzing with computer programs and artificial intelligence that makes the whole process quicker. As I said before, water authorities need and do have proactive, comprehensive plans, but these plans may take 5, 10, 15 years to implement. And again, please remember, valves don't always work, and they need to work when repairs and outages are being implemented. So on my last slide here, it's all about the water. It's a valuable resource. We want to preserve our infrastructure and make it last. Supply of water needs to be sustainable. Some of our groundwater levels are dropping drastically low out west. But we want to maintain the public trust. When anybody with a water authority is investigating and repairing sections, communicating that to the clients, to the people that use the water, is very important. And spending those resources wisely is incredibly important. But these programs take time, okay? This could be 5, 10, 15 years. Maybe there's elected leaderships in a town or county or water authority that changes. And the most effective and successful programs are where there's buy-in at the highest level and good communication with all the customers. But the main takeaway here for this afternoon, there it is. It's expensive. And there's a wonderful article that I found in the Wall Street Journal about 6 years ago, War Beneath the Streets, Fighting to Replace America's Water Pipes. Ben, I'll open it up for a few questions and see where we stand here. Hopefully our timing is good. What do you got?
Excellent presentation there, Bill. Yeah, we got some questions rolling in. I do want to remind everyone to make sure you do have your name along with your question there. Make sure that we can contact you after the show to get you considered for the gift card. So we'll start off with Brendan's question here. For the acoustical impact testing of the reinforced concrete wall that was shown, why is the nitrogen used to generate the impact force in the tool, and why not use compressed air?
Well, nitrogen is compressed air. It's a cheap compressed air. What we want is the same pressure in the tank. So every time we're inducing an energy source into the pipe wall, it's the same energy. It's a repeatable energy source. We use the same steel bearing, so the mass is the same. As long as the pressure in the tank is the same, we could use compressed oxygen or compressed hydrogen or whatever we wanted. Nitrogen is a little cheaper, but it's the same pressure that we need to have consistent energy introduced into the pipe. Good question.
Very good. From Ahmed, is there a limit to the distance capabilities for through testing?
You know, that's a great question. There really isn't. In a non-pipe application, we were testing with divers through a tremie pour of a very large signature bridge. And that was about 30 feet across the tremie seal foundation pour, if you will, the first one. Again, with through testing, you need to have accurate X, Y, Z coordinates on both sides of the member that you're testing. We had that, and then we had one diver on the left side of this tremie pour, another diver on the right side of the tremie pour. Was initially formed with steel sheet pile, so it was kind of a W shape, and we were able to go through. It was 30 feet long. Once we had that through testing profile, then we cut it. We set up a tomographic image and slice tomograms, and based on the velocity, get the concrete compressive strength at different slices, 2 feet in, 3 feet, 5 feet, 6 feet, 10 feet, whatever it may be. What the medical community does with our heart or our brain or our spleen, they do ultrasound around the perimeter and then slice it. Go ahead. Any other questions, Ben?
It's easier for me to ask them if I unmute myself. From Caleb, are there permanent systems that NDT can install to monitor concrete strength, or is this a procedure that needs to be revisited each month, year, etc.?
It needs to be revisited, and then sometimes you can see if there's deterioration that's occurring in the strength. If we had 6,000 PSI 1 year and come back 3-4 years later, and now it's 4,500, now we have 2 points in time. We can start to understand and predict how that service life or the rate of deterioration is going to occur over time.
And I think this question kind of builds on that one. Can you expand on the details for long-term monitoring and how that would be done?
Yeah, again, long-term monitoring, kind of two components to that. One would be the testing that we talked about, the mechanical testing, where we have a point in time and then test the same section of pipe at a point later in time and compare the two. The other is some monitoring of equipment that's actually mounted inside the pipe. It's kind of like a fiber optic cable that is mounted along the inside of the pipe, and it listens for breaks, wire breaks primarily. And when they hear a pop, that impacts the fiber optic transmission within the cable, and they can record the number of wire breaks and get the relative location of the wire break. So testing the pipe sections at different points in time, and then the continuous monitoring is a little bit more involved to set that system up, but that helps with the program to prioritize where certain sections may be deteriorating very rapidly.
All right. And can the energy projectile gun testing apparatus damage the pipe?
Good question. No, it does not. Whether it's on the inside or the outside, it does not damage the pipe. However, if we're testing on the outside of the pipe, sometimes the soil that might be the confining pressure on the pipe, and by removing that soil, you may be weakening the pipe itself. So sometimes when we're doing testing of the outside of the pipe, it may be very advantageous to talk to the water company and reduce the pressure, make sure there's no surges in lines where we are actively testing the pipe from the outside and have dug down 3, 4, 6, 8, 10 feet. So that soil can kind of be a protective layer, even if there's wire breaks and even if the pipe is compromising, that soil, in essence, may be kind of keeping it together. So you have to be aware of that.
All right. How do the threshold limits for normal conditions get defined?
That's a good question. It really comes down to years and decades of experience. We've been testing pipe now for well over 20, 25 years. We've tested good quality pipe. We've been asked to do forensic investigation on failed sections of pipe. So we know what the velocity or what the frequency should be in good quality pipe, and it really comes down to our experience that we have internally to know where the threshold of where a moderate condition reduces the strength of pipe and where that monitor or moderate condition may advance to a severe condition. So really think the answer is experience and working within the industry and testing different sections of pipe that we know are in good condition and that we know are in failed or poor condition, and then defining those thresholds, working with other engineering firms on what those thresholds are.
All right. Gorcam, can soil and temperature affect the signal data that you get from your measurements?
I'm assuming that's now testing from the inside. If the soil temperature, not as much. Soil on the outside, better yet, if there's a concrete, I'll call it a saddle. Sometimes these larger diameter pipes are sitting kind of in a concrete saddle or a very almost designed bedding material. So yes, the material that's on the outside, and if there's voids on the outside, we can get a different echo response within the pipe if there's a void, or if it's got a concrete saddle behind it, or if maybe that concrete saddle has failed a little bit. Temperature, not as much. Great question, Gorham. Thank you.
We got one from Anonymous, so hopefully they reply with their name, but this may relate to a previous question, but what kind of depth limitations exist with GPR testing? Say a storm drain 8 to 10 feet below the ground surface, what issues might you have?
That's a good question. A lot of my answers for GPR is it depends, because it really does. Under ideal, dry, granular conditions, some of the low frequency GPR, very successful at getting data 8 feet deep, 10 feet, 12, even 14 feet deep. Now, if it's a saturated clay or silt, that's going to be reduced. And if it's a saltwater groundwater table or a brackish environment where there's been some salt residue in the soil matrix, that could cut that way down. Salt is conductive, and we might only be able to penetrate 3, 4, 5 feet in some instances. So usually it depends, but ideally low frequency, we can get 12, maybe even 14 feet of penetration. And then you're reflecting off the pipe or the anomaly or the rock or the whatever the case may be.
Do you have any special considerations for inspection of joints or connections when you're doing your non-destructive testing?
That's a good question. The joints are a failure mechanism. You can have water starting to work its way through there. They can also be cracked during installation. I wouldn't say there's anything special at the joints, but we do spend special attention at the joints, making sure that we visually look at them. They're every 16 feet or every 20 feet or whatever the pipe sticks are. So we do want to look at them more closely, and then maybe we do a little hammer sounding closer around then. Our hammer sounding is a follow-up to where we find some anomalies, and then we want to delineate where the limits of those anomalies exist.
All right, I think we got time for 1 or 2 more questions. What is one proactive thing that owners and engineers can do to add value to their pipe systems?
Boy, I get asked that a lot. I would say if, a water authority has a program out there to identify the condition and assess all these pipe systems, every time there's a maintenance crew that's out doing something somewhere, boy, it'd be great to document what they find and make sure that gets back to the project manager or the consultant that is doing the condition assessment, because there's always maintenance going on. What are the conditions? What is the diameter of the pipe? As-built conditions are not always design conditions. So when the crews are out there, make it a point to record the information and then put it in a place where the pipe system condition assessment team has access to it. That's a great question, Ben.
All right, Bill, I think we are out of time for our Q&A section. Excellent presentation. If we didn't get to your question, or if you think of any more, Bill's contact information is going to be on screen here. Just one moment. I'll get it visible.
I got it up if it's there, or you got control. Go ahead, Ben.
About that. So yeah, there's his information on screen. Email him or give him a call. His details will also be included in our post-event email, along with links to the recording and the slides. Next month is our webinar Wednesday non-destructive testing series with Keith Holster. So he's doing subsurface secrets, geophysical methods for infrastructure renewal. That's on July 19th. He's going to be showing you how to get insights on the piles, soil layers, sinkholes, and hidden structures, I believe using more GPR technologies. Here's some kind of sneak peek images that likely will be included in his presentation. Bill, do you have any teasing you'd like to do on his presentation?
Yeah, you know, just a little tease, a lot of pile testing, timber, steel, concrete piles will be discussed, borehole. There's testing methods that can be done from a cased borehole, in between boreholes. So lots of exciting stuff, and hopefully everybody can join us in 3 weeks. Excellent.
Well, thank you, Bill, for this awesome presentation.
Wonderful. Thank you, everybody, for spending an hour here to talk about pipe streams on pre-stressed concrete cylindrical pipe. Appreciate your time.
Exactly. Thank you all for coming, and let's get out there and save some structures.
Have a nice day. Thank you.